Now let's talk about how we would handle lines of charges in Coulomb's law. Let's consider our xy case, like this, and let's consider a line of charge that goes right here from 0 to y equals 3, and every place on that line of charge, my charge distribution rho L for line charge is going to be given as 7y coulombs per meter. You can tell it's a line charge because it's coulombs per meter, and right here what this is telling us is as we get higher, closer and closer to the top of this wire, the charge increases. That would be consistent because our charge does concentrate on the end of wires. And we want to know the electric field right out here at the point where x is 4 and y is 3. So the way we do this, because we have a distributed charge, is we're going to break it into little teeny pieces of charge and pretend that we add up each of those charges individually. Of course, adding a distributed system like this is equivalent to integration. So each of these little pieces, each of these little lengths, is going to be a dl, just a small differential unit of length that's going to be a little piece of our charge. Over that little differential unit of length, we can assume that our charge is constant because it is so small. Now we're going to follow our process exactly the same way we did before. The first thing that we need is an origin. There's my convenient origin. And then we need the vector rs. Rs is the vector from the origin to the source or to the charge. But right here we can see that there are several different places where we have charge, so we're going to just choose one of them, someplace along here, and write our vector rs. Rs is 0 in the x direction plus some value in the y direction. So right here is the y value. I'm going to call that ys because that's telling me the y location of that little piece of source. We then need a vector rp. Rp is the vector from the origin to the point where we'd like to measure the field. In this case, it is 4 in the x direction plus 3 in the y direction. We then need a vector rsp, which is the vector from the source, my little piece of source, to the point of interest. That is rsp. That is rp minus rs, which is 4 in the x direction plus 3 minus ys in the y direction. Now let's see how to apply Coulomb's law. We're going to apply the differential form of Coulomb's law, which says a little bit of electric field caused by this little bit of charge dq over 4 pi epsilon, the magnitude of rsp squared in the unit vector direction from the source to my point. Well, I need two things here. I need rsp, which is the magnitude of my rsp vector. The way I find that is I just square all the components and take the square root, like this. And then I need the unit vector rsp, and that's going to be equal to the vector rsp divided by its magnitude. That's the definition of a unit vector. So it's going to be 4x plus 3 minus ysy, all divided by square root of 4 squared plus 3 plus ys squared, like this. So now we have everything that we need to be able to put into this equation. The next thing that we're going to do is actually find the electric field by adding up all of these little differential elements of length. The way we do that is we say that the electric field is the integral over the length of dE. So that's equal to a length integral from ys equals 0 to 3, this value 3 right there, of dq. And what is dq? dq is rho L times dl over 4 pi epsilon rsp squared, unit vector of rsp. We'll come back to this in a minute.